so we're going to have a look at the different standing waves, different harmonics, different overtones that we can set up in open and closed pipes. Let's have a look at open pipes first, and remember that always at the open end of a pipe we have an antinode. So we start by drawing that on. The simplest form we can draw must have one node in the middle. And so our simplest one just looks like that. Now the eagle-eyed amongst you will spot that that's really similar to our fundamental wave on a string. It's just we've kind of split it in the middle and turned it round to face the other way. And so that means that all of the maths is going to be the same. Look, for the fundamental wave, for the first harmonic, the wavelength is twice the length of the pipe. If we bump up, the next simplest one we can make has got two nodes. It's still got an antinode at each end. That means the wavelength is the pipe length for the first overtone, second harmonic. If we come up to the second overtone, which is the third harmonic, then the wavelength is 2/3 of the pipe. Over here, at the third overtone, the fourth harmonic, the wavelength's half the pipe length. And finally, it keeps going for a lot longer, right? Up to infinity, but we'll stop at 5. The fifth harmonic, which is the fourth overtone, the wavelength is 2/5 of the pipe length. And so that maths is just identical to what we looked at with waves on strings. Okay, let's now move on to what do the standing waves, the overtones and the harmonics look like inside a closed pipe. Remember, our rule for a closed pipe is that there's always going to be a node at the closed end and an antinode at the open end. And so our simplest wave form is just like that. How much of a wave is that? That's 1/4 of a wavelength. And so that means that the length of the pipe is 1/4 of a wavelength. That means that the wavelength is 4 times the pipe length for that fundamental wave, that first harmonic. And then it's really easy for the second harmonic, the wave length, we have to double the frequency, and so we have to halve the wavelength. We're just going to make that wave half as long. Look. Oh, that doesn't look right, does it? We've got a node here, and we're meant to have an antinode here, but if we halve that wavelength, we end up with a node here. That's all wrong. In fact, it's not possible. We can't double that frequency in a closed pipe. It can't work. If we try to double it, we end up either putting a node at the closed end, or a node at the open end, or an antinode at the closed end. And so it's just a no-can-do situation. But we must be able to make something higher. Let's have a look. What about if that node is 1/3 of the way along the pipe? Now that looks like it meets the requirements, except that now we've got 3/4 of a wave when we used to have 1/4. That means that we've got 1/3 the wavelength. That means 3 times the frequency. That's the third harmonic. But by the quirk of physics, that means there's nothing that can play here. It's the third harmonic, but it's still the first overtone, because we can't play any other note in between this one and this one. Looking at that wave there, we've got the wavelength is 4/3 the length of the pipe. That means that our pipe length is 3/4 of the wavelength. And the next one, now if we try to make the fundamental wave to be 1/4 the wavelength, 4 times the frequency, we're going to find ourselves banging into this same problem here. Look. And so we're back to that place of no can do. It's just not possible. We're trying to make a node occur at an open end or an antinode occur at a closed end, and that's just not possible. That's physically impossible, so that resonance does not happen. This one does. And it looks something like that. We managed to squeeze in 2 notes, and you've probably spotted that we're up to 5 times our original frequency, 1/5 of our original wavelength. So we're going to call this the 5th harmonic, but it's only the 3rd overtone, only the 2nd overtone. It's the 2nd possible note above the fundamental that we can play. And so the wavelength is equal to 4/5 of the pipe length in that case, or the length of the pipe is 5/4 of a wavelength. A little bit more confusing than the open pipe, but it's okay, we can cope. We just remember that we can't do the 2nd one, and we can't do the 4th one. In fact, we can't do any even ones. We can only form the odd harmonics on a closed pipe.